Hi, welcome back to another in-depth game development video series. In this next set of videos, we're going to be talking about pathfinding. In this first part, we're going to explore what pathfinding is and define some of the concepts we'll need to know to implement them. And in subsequent videos, we will explore some different pathfinding algorithms and how you can implement them in your games. But first, let's talk about what we mean by pathfinding. So I have a simple Pygame program here that just draws a grid that's going to represent our game screen and the map that we're going to be moving around on. Before we start writing any code, we need to talk a little bit about how we're going to represent the data for our map. And pathfinding algorithms work on something called a graph. And a graph looks like this. A graph is a mathematical construct where you have nodes, that's what these circles are, and the nodes have connections between them. And if you notice, these connections have arrows on them, which means they are directional. From A, you can travel to B, but from B, you can't travel back to A. And pathfinding algorithms work by traversing the connections in the graph and finding the path from your desired starting point to your desired ending point. For example, if I am starting on E and I want to travel to A, then the path is going to be to move to D, then to B, then to C, then to A. And so a pathfinding algorithm, the inputs would be the start and the end, and it would tell you the list of the connections that you have to travel to get there. And so in most 2D games, we're representing our map as a grid of squares. And so your graph could be a grid that looks like this, where each tile on the grid is a node, and the connections are all of the edges. Each node is connected to its adjacent neighbors. And this is fine. This works fine from here. You can travel along this path to whatever other node your destination is. And for example, if you wanted to have some walls, then your graph would look like this, right? And so the path would have to go around the walls if you wanted to get from one side to the other. However, something that you need to take into account is that graph algorithms are faster when there are fewer nodes. So the more nodes you have, the longer it's going to take to calculate all the different paths and find the shortest one. So for example, let's look at this map. So here's a map of tiles. This map is 640 tiles, 32 by 20. So if we were using a square grid, the pathfinding algorithm would have to look at each one of these tiles and all the connections between them to get from any point to any other point. But we could make this a lot more efficient if we thought about the fact that if you're starting in this room over here and you're heading for this target, the difference between this tile and this tile, the path is going to be almost the same. So you might want to represent your pathfinding graph like this, just using nodes where there are doors or in the middle of the room, right? And then now we only have 22 nodes in our graph instead of 640. So this is going to be a lot faster to calculate. And so if your mob was, say, over here in this room, and your target is over here, then you would just say, travel towards the nearest node, and then follow the path on the grid, on the graph, and towards the closest node to the target. And then your mob would find from wherever it is what the shortest path is towards that target, and then it would be close enough to go straight towards it. And we'll talk about that a little bit later once we have our algorithm set up and we're starting to do some pathfinding. But to start with, just to keep things simple, we're going to stick to the square grid representation so that our graph, our pathfinding graph, is going to match our map grid. We will talk a little bit later once we have it working about how we can do this kind of optimization. Okay, it's a little bit more abstract, so we're going to stick to this representation where our map is going to be a grid, our walls are going to be blank grids that you can't travel in, and our pathfinding algorithm will just look at all the tiles individually. Okay, so our task will be to represent this data in our code. So our grid is going to be a bunch of squares, right? And they will just be labeled by their grid position. And any tile that's a wall just shouldn't be in the grid at all, right? If there is no 2, 1, then there's no way to connect to it. So we'll just keep a list of the walls, and those will be the ones that we ignore. Every other tile we look at. And any tile that we have, we just need to be able to calculate what its neighbors are, right? Which if it's in the middle, is going to be all 4. But if we're on an edge or in a corner or near a wall, we need to make sure that we only connect to the adjacent ones. So we'll need to be able to calculate for any given tile what are its neighbors. Okay, so we're going to do that by setting up a new object or a new class. So we're going to call this a square grid. And its starting parameters are just going to be, we're going to tell it what width and height we want. And we'll store those as properties so that we can access them anytime we want. And then the walls are just going to be a list. It'll be a list of what tiles have walls in them. Okay. I'm also going to make a list here of what connections are allowed. And what I mean by that are which directions from any given tile, which directions can you travel in. Okay. And in the grid that we drew, obviously you can move up, down, left, and right. And so since our nodes are going to be our handy Pygame vectors, we're going to make a list of all the directions that you can travel in. You can travel to the right, you can travel to the left, you can travel up, or sorry, down would be +1, or you can travel up. Those are the 4 directions. Now, if you were to be on a grid where you allowed diagonal travel, you could add those as well, right? You could add 1, 1, and say you could travel down and to the right, and so forth. But we're not going to do that. We're only allowing up, down, left, and right. And that'll help us calculate what neighbors a given cell has. Okay. And that's what we need to do next, is we need to calculate, we need to find the neighbors of any given node. Right, so if we pass a node, what are the neighbors of that node? Well, the neighbors, to start with, the neighbors are going to be taking this node and adding each of these vectors to it, right? And we'll get 4 neighbors. So we want to take the node plus connection for each connection in that list of connections, we're going to add it to node. And then we're going to have a list of vectors at the end of this that has those 4 in it. And that's fine, except for the case where, you know, 1 or more of these isn't legal because we were on an edge or we were next to a wall. So we need to take these 4 vectors that we have and we need to filter them out. We need to filter out the ones that are in the walls or outside of the bounds. And the easiest way to do that in Python is using the filter function. So there's a function called filter in Python. It takes 2 arguments. Okay, the Second argument is what sequence you're filtering, right? We're going to filter the neighbors list. And the first argument is what function you want to apply to that to filter it out. And this function will be a function that can return true or false, right? So if it looks at the list, applies some criteria that can result in true or false, and then what you get back out of the filter list, or out of the filter function, is which ones were true, right? So we have a couple of things we want to check. First, we need to just check if that node that we're adding here is inbounds, right? Is it a inbounds move? So let's define a function called inbounds, right? Just to check if a node is in the bounds of the grid. And what that means is, if we have a grid that's 10 tiles wide, then the legal values for x are from 0 to 9, right? And for y, it's between 0 and height minus 1, right? So we just need to check if that is the case. And we can do that by just saying, my cursor, if we just want the x to be between 0, less than or equal to 0, and less than width, but not equal to, right? And also the same is true with y. Right? If both of those things are true, then the tile is inbounds. That node is inbounds. So we'll use that, inbounds, and we'll just assign that back to neighbors. Okay. So now our neighbors list, instead of having all four in it, we'll have just the ones that were inbounds. Okay. Now we need to do the same thing again to filter out if it's a passable tile, meaning there's no wall there. Right, so let's define passable. And this just means tell us if it is node not in walls, right? As long as the node is not in the walls, then we're good. Oop, I just noticed I just put x, but that's supposed to be node.x and node.y. Okay. So now we should have a list. Let's print it out just to test and be sure it's true. What we really want to do is return it. Right, but let's print it out so we can see if our make sure our filters are working, right, and we're finding the neighbors. So we can test that out. I've actually already gone down here and I've created a square grid that's 5 by 4, and I've added 2 walls. And that's actually so that it will match exactly what we had here in our little example. Right, I have walls at 2, 1 and 2, 2. Okay. So I've created that grid that's 5 by 4 and added those 2 walls. And now let's find the neighbors of 0, 0 and the neighbors of 3, 2. And hopefully we'll get the right answers. Let's see what happens. Okay. Oh, so you see when we print, we're printing out and it's printing a filter object. Okay, what that means is when you run the filter command, or when you run the filter function, what it returns is a filter object, which is an iterable, right? Which is something you can loop over and do things with, but you can't just print it out directly. So we need to print out that as a list. Okay, so that's our problem there. All right, there we go. So the neighbors of 0, 0 are 1, 0 and 0, 1. So you can see it filtered out -1, 0, and 0, -1. And then the neighbors of 3, 2 are everything but 2, 2, right? So it didn't include 2, 2 because 2, 2 was in the list of walls. Okay, so our neighbor function is, our find neighbors function is working. So let's just not print that out. Okay, then the last thing I'm going to add to the square grid here so that we'll be able to see it is just a draw method. I'm just going to draw the walls where they're supposed to be. So we're just going to go through the walls and figure out where their rectangles are supposed to be. It's going to be a rectangle at node, or sorry, at wall times tile size, right? That's going to give us the location because wall is a vector, so it's going to give us the x and the y. And then the width and height are just also tile size by tile size. And then we just pg.draw.rect screen, and that light gray color, that rectangle. So that way we'll be able to draw them. We can test that out just by doing g.draw, and we should get a couple of walls at 2, 1 and 2, 2. Okay, so let's get rid of this test grid, and what we're going to do is we're going to make it the size that we specified up top, grid width by grid height. So that's going to be how big our grid is. And we need to be able to add and remove walls. And the easiest way to do that is going to be able to click on the screen and draw walls and remove them. So we want to detect mouse clicks. So in our event loop here, we're going to say if it's a mouse button down. So if it's a mouse button down event, then we need to get the mouse position, right? And that's going to tell us what screen coordinates our click was at. But let's make that a vector, since we are going to be working with vectors on the other ones. Now we have the x and y on the screen of where the person clicked, right? But we want the tile coordinates, so we need to divide by tile size, and then we'll get the integer values, right? Because we're doing integer division. And so now we can say if event.button equals 1. So if we clicked with the left mouse button, then whatever tile we've clicked on, we want to, if there's no wall there, we want to add a wall there. But if there is a wall there, we want to delete the wall there. So we want to just basically toggle walls. So if it's in the walls list, then we want to remove it. Right? Otherwise, we want to add it. Okay? And we're drawing them, so we should be able to click and add walls now. Okay? And so you can go along and add and remove walls however you like. Perfect. Okay. All right, and we are done. We have everything we need to create our graph, to add and remove walls so that we can test the pathfinding and see how the paths change as we add and remove walls. And in the next video, we will start building our pathfinding algorithms. We'll start with simple ones, and then we'll improve them as we go. All right, thanks for watching, and I'll see you in the next video.